Hi everyone, this is Professor Mayunger and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started. Hello viewers, today I'm going to show finite element analysis of a bar which is having constant temperature at one end, and from other end we'll be providing heat flux at a specific rate, and that will be done using ANSYS mechanical APDL. And finally we will validate these results using theoretical calculations using finite element analysis. Okay, let us see the statement of the problem. The fin shown in figure is insulated on the perimeter. The left end has a constant temperature of 100 degrees centigrade. A positive heat flux of 5000 watt per meter square acts on the right hand side. Thermal conductivity of the material is 6 watt per meter degree centigrade, and cross sectional area of this one is 0.1 meter square. Determine the temperatures at L by 4, L by 2, 3L by 4 and L, where L equal to 0.4 meter. So the problem is clear. That means we are having a bar which is having temperature of 100 degrees centigrade at left hand side. On the right hand side we are providing a thermal flux of 500 watt per meter square. The cross sectional area of this one is equal to 0.1 meter square, and we need to determine temperatures at a specific length of L by 4, L by 2, 3L by 4 and L. Total length equal to 0.4. So we need to find out the temperatures at 0.1 meter, 0.2 meter, 0.3 meter and 0.4 meter from left hand side. Right. It's clear that if you want to analyze this one using ANSYS finite element, the length of the bar will be 0.4 meter, and at a specific distance of 0.1 meter, 0.2 meter, 0.3 meter and 0.4 meter, we need to find out temperatures. This problem cannot be solved using link. This is a completely different type of problem. As we are providing heat flux from the right hand side, it cannot be applied on a specific node. We need to have either more than one node, or you need to have a specific surface to apply heat flux from any specific surface or from any specific line. So we need to model this one a little different way compared to the normal method, right? So without wasting time, let us start our analysis using ANSYS mechanical APDL. The bar is insulated, that means it is not having any kind of convectional effect, right? So first of all, we need to create a directory, and in that directory we need to save the work, whatever we are doing, that to be saved, everything there in the directory itself. Next to that, we need to change the title of this project. Let us start with file and change title. We are keeping the name of the title as FEA 11. Okay, and to see the title we can click on plot replot. It will show the title at the lower left corner. Next to that, we need to select what type of analysis it is. That will be coming from preferences, and definitely it is a thermal analysis. So thermal analysis checked in. Okay. Next to that, we need to select elemental properties, and that will come from element types. Add, edit, delete, add. In this case, I told that it is not a normal problem. It is a little bit different compared to the normal problems. So we cannot consider link. We need to consider something else as an element, right? We're considering solid, and by default it is taking quad 4 node 55. Okay. From options, we can select element behavior. We can select this one as plane thickness. Okay. Let us close it. Now in this case, it is provided that it is having cross sectional area of 0.1 meter square. It is not mentioned that whether it is a circular or rectangular or a square. So we can decide ourselves. We'll provide some specific thickness from here, and we'll provide the height of that one accordingly. Right. From real constant, we can provide the thickness of this one. Add, edit, delete. Let us add it. Let us provide thickness of this one as 0.5 meter. Okay. Close. As we have provided thickness of 0.5 meter, so definitely to have a cross sectional area of 0.1 meter square, we need to have the height of that one as 0.2. Right. Okay. That will be done later on during modeling. Next to that, we need to provide material properties, material models. It is having single model with thermal conductivity 6 watt per meter degree Kelvin. So thermal conductivity isotropic, and it is 6 watt per meter degree Kelvin. Okay, done. Let us close it. Next to that, we need to start modeling. Create nodes in active coordinate system. Now the thing is, while creating the nodes, we have to be very much cautious that for a specific element we will create 4 different nodes, because it is having some specific area of 0.1 meter square. We have already provided thickness of that one as equal to 0.5 meter, and we need to provide a height of 0.2 meter. So for each element we are planning to have 4 different nodes, right? Let us provide this one by one. Total length of the bar equal to 0.4 meter, and at 0.1 meter away we need to have different elements or different nodes, right? Let us create first node at the origin. So apply. Second node will be created at a distance of 0.1 meter. Apply. Third node will be created at a distance of 0.1 meter, and let us consider height of this one is be 0.2 meter. Apply, and again, as each element is consisting of 4 nodes, another node to be created at a distance of x equal to 0 and y equal to 0.2 meter. Apply. This is made. Next node will be made at a distance of 0.2 meter. Apply, and along y also we need to make this one. So along y it will be again 0.2. Apply. Next node will be created at a distance of 0.3 along x. Apply, and next one it will be at a distance of 0.3x, and along y it will be 0.2. Apply, and the last one it will be created at a distance of x equal to 0.4 and y equal to again y equal to 0. Apply, and the last one it will be at a distance of x equal to 0.4 and y equal to 0.2 meter. Okay, we can see we have created actually 10 defined nodes, and these 10 defined nodes will be consisting of 4 different elements, right? First element will be comprising node number 1, 2, 3 and 4, and let us make elements auto numbered through nodes. Let us join node 1, 2, 3, 4. Apply. First element is made. Now we need to apply the second element combining node number 2, 5, 6, 3. Join 2, 5, 6, 3. Apply. Second element is also made. Now we need to make the element 3 with the corresponding nodes as 5, 7, 9, 6. Apply, and finally the last element, fourth element, will be comprising of node number 7, 9, 10 and 8. Let us join 7, 9, 10 and 8. Okay, we made all the elements, right? So next to that we need to apply boundary conditions that will be coming from loads. Analysis type, new analysis, and it is a steady state analysis. Now we need to define loads. Apply thermal temperature at nodes, right? And we know that at left hand side we are having a specific temperature, and at right hand side we are providing some heat flask at a rate of 5000 watt per meter square. And from left hand side we are having a temperature of 100 degrees centigrade. So select node number 1 and 4. Okay, and temperature will be 100 degrees centigrade. Apply, and right hand side you need to have a heat flask of 5000 watt per meter square, right? So heat flask on nodes, select node number 9 and 10. Okay, now we need to have a constant heat flask of 5000 watt per meter square. Okay, done. So we applied our boundary conditions. Next we need to solve it. Solution, solve, current ls. If everything is right, it will show solution is done. Okay, solution is done, so our result is ready, and we can see our results from general post-processing, right? We'll see our results from general post-processing. Plot results, contour plot, nodal solution, degrees of freedom solution, and we're going to see nodal temperatures. Let us see it. So these are the temperatures at different nodes. You can see it. The minimum temperature is 100 degrees centigrade and maximum temperature at the right hand side, from where we have applied a heat flask of 5000 watt per meter square. At that node temperature is 433.33 degrees centigrade, right? And in between we are having different temperatures at different nodes. And to have the temperature at different nodes, it is better to see this one in the form of listing results, right? So let us see the results from list results. List results, nodal solution, tube solution, and nodal temperature. Let us view it. So these are the results, and to understand the results in a better way and see the model also, they need to be easily understood, right? Plot nodes. These are the nodes, and we can provide specific numbers to these nodes. That can be done from plot controls, numbering, and the node numbers you want to make it on. It will show the numbers of nodes here itself. Like at the lower left side, node 1 and 4, you can see temperature is actually 1 and 4. The temperature is actually 100 degrees centigrade. This is the extreme left hand side. There we are having constant temperature. 1 and 4 is having constant temperature 100 degrees centigrade. Actually our result is expected at node number 2, 3 node number 5, 6 and 7, 8. These are the 3 set of results we are expecting, right? Node 2 and 3, this is in the first element itself. In node number 2 and 3, you can see the temperature is actually 183 and 183. So node number 2 and 3, we are having constant temperature 183. This is our desired result. Similarly, for the next set, at a distance of 0.2 meter, the node number will be 5 and 6. At 5 and 6, we are having the temperature of 266.67 degrees centigrade. And at a distance of 0.3 meter from the left hand side, the node number is 7 and 8. Their temperature is 350 degrees centigrade. So these are the results we are expecting, right? We can save this one. File, save as. In the desktop, we are saving this one. This is very important one. So we got our results at a distance of 0.1 meter. We got the temperature as 183 degrees centigrade. That is the node 2 and 3. And at a distance of 0.2 meter, that is node number 5 and 6, temperature is 266.67 degrees centigrade. And at a distance of 0.3 meter from left hand side, that is node number 7 and 8, temperature we got 350 degrees centigrade. These are the results. Okay. Now we have to validate our results using theoretical calculations. Okay. So let us close this one. So this was the question. The fin shown in figure is insulated on the perimeter. That means we are not having any kind of convection. The left hand has a constant temperature of 100 degrees centigrade and a positive heat flux of 5000 watt per meter square is applied at the right hand side. And we need to find out temperature at the specific locations of at a distance of 0.1 meter, 0.2 meter, 0.3 meter and 0.4 meter from the left hand side, right? To have this answer theoretically, we need to have the finite element model of this one. And let us see the finite element model of this one. So what we have done is we have segmented this one into 4 different elements with 5 different nodes with having temperature T1, T2, T3, T4 and T5, right? And the distances from left hand side is already 0.1, 0.2, 0.3 and 0.4. From left hand side, we are providing constant temperature of 100 degrees centigrade, and from right hand side, we are providing a heat flux of 5000 watt per meter square. So what we have to do, as per normal practice, we need to find out 4 different elemental stiffness matrices, K1, K2, K3, K4, right? Let us do that one. We are having elemental stiffness matrix equal to K1, first elemental stiffness matrix. We are providing all these values, A equal to area, K equal to thermal conductivity and L equal to length. In all cases, we are having same thermal conductivity of 6 watt per meter degree Kelvin. Similarly, for second case also, we can see area is also same. As it is the same cross-section area, in all cases we are having same elemental stiffness matrix K1, K2, K3. This is K2 and this is K3. And finally, this is K4. All cases we are having same thing because the cross-sectional areas and also length all are equal. Next to that, we need to combine all these different elemental stiffness matrices to get the value of global stiffness matrix, right? This is known as global stiffness matrix. And in this case, this 1C, 2C, 3C, etc. These are very important numbers. These are known as GDOF or global degrees of freedom. This is required to combine all the different elemental stiffness matrix to a global stiffness matrix. Next to that, what we have to do is we have to follow the equation Q equal to T into F. This is the global stiffness matrix. This is temperature. This is F, right? Now applying all these values of F1, F2, F3, etc., we can find a different set of equations. This is a 5x5 matrix, and we can reduce this matrix to 4x4 by applying required boundary conditions. You can reduce the matrix to 4x4, and then finally we are getting 4 set of equations, right? And from these 4 set of equations, you can find out the temperatures at T1 equal to 100 degrees centigrade, T2 equal to 183.3 degrees centigrade, T3 equal to 266.63 degrees centigrade, T4 equal to 349.96 degrees centigrade, and T5 equal to 433.297 degrees centigrade. It is exactly same what we got in case of our finite element analysis using an ANSYS mechanical APDL. So our ANSYS mechanical APDL result is completely validated using theoretical analysis by finite element method. Okay. So with this one, we'll conclude our today's video. This was a very simple analysis of a bar in which we have applied a constant temperature from left hand side, and from right hand side we have provided a constant heat flux. And in this case, we got temperature distribution at different locations. Okay. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.